We've just added the binomial coefficient to our list of tools for solving complex counting problems. The binomial coefficient n choose k counts the number of ways to select a group of k things from a larger collection of n things. An important interpretation of this is it's the number of ways to choose a k-element subset of an n-element set. One important thing to remember about sets in general is that the ordering of the elements in a set doesn't matter. But what if we're making a selection from a larger group and the ordering did matter? That's what this video is about. Let's start with a simpler situation. Suppose I'm playing a game where I have some letter tiles and I need to rearrange them to spell out as many words as I can. Suppose that I have 7 of these tiles and they're all different letters. How many arrangements are there? That is, how many ways can I reorder this set of tiles? We can solve this pretty easily with the multiplicative principle. Imagine that I'm going to physically reorder those tiles on an empty rack with 7 positions. Filling the empty rack is a sequence of choices, so let's count the choices at each stage. There are 7 ways to fill the first slot, 6 for the second, then 5, then 4, then 3, then 2, then 1. So the number of rearrangements is the product of all these, which in this case is 5,040. You might remember that this product of 7 times 6 times 5 and so forth times 3 times 2 times 1 is called 7 factorial. More generally, if I had n tiles and they were all different letters, then the number of rearrangements would be n factorial, n times n minus 1 times n minus 2 times, and so on down to 3 times 2 times 1. In fact, n factorial in general counts the number of ways to rearrange any possible list of n distinct or different objects. Now let's think about the problem we started this video with, counting the number of ways to select a group of objects from a larger group of objects in such a way that the ordering actually is taken into account. Again, if the ordering were not taken into account, we just use the binomial coefficient, because that's just forming a subset from a larger set. Here's an example of the kind of problem we're interested in. Suppose I have a class of 12 students, and from that group I need to pick 3 students to be the leadership team of the math club. One student will be the president, another the vice president, and the other the treasurer. How many ways are there to make this selection? You might be tempted to say the number is 12 choose 3, but that wouldn't be correct because that would treat the choice of Alice as president, Bob as vice president, and Chuck as treasurer as the same choice as Bob as president, Chuck as vice president, and Alice as treasurer. So let's think about this. Imagine the 3 leadership team choices as 3 spots to fill, because it is 3 spots to fill. Filling those spots is a sequence of choices. There are 12 ways to fill in the first spot, then 11 ways to fill in the second, then 10 to fill in the last one. So the correct number of ways to make the selection is 12 times 11 times 10, which is 1,320, and that's just using the multiplicative principle. We could just stop there and say this problem of selecting an ordered list of objects from a larger group always works out like this, just using the multiplicative principle, and it wouldn't be wrong. But let's look a little further. This number 12 times 11 times 10 is not a factorial, but it is a piece of a factorial. In fact, if you think about it, it's 12 factorial with 9 factorial divided off. So the number of ways to make this selection could be phrased as 12 factorial divided by 9 factorial. This looks a little like the closed formula for the binomial coefficient. 12 choose 3, which was a wrong answer, according to that formula would be 12 factorial over not just 9 factorial, but over 9 factorial times 3 factorial. So this ordered version of the binomial coefficient is missing the 3 factorial on the bottom. And that makes sense because we're taking the ordering into account now. The binomial coefficient, when we were defining it a few videos ago, divided off the 3 factorial because choosing items with the ordering counted each arrangement as different selections. That was not what we wanted when we were making subsets, so we divided off the 3 factorial to correct the count. But this is what we want when we are making ordered selections, so we don't divide it off. In general, when you make a selection of k elements from a larger group of n elements and do so in a way that takes the ordering of the choice into account, this is called a k-permutation, and this is denoted p of n comma k. We just learned that p of n comma k is always equal to n factorial divided by n minus k factorial. For example, we saw that p of 12(3) is 12 factorial over 9 factorial. And this isn't some magical formula, it's just the multiplicative principle at work. Here's another example. Suppose I have a set A with 4 elements and a set B with 10 elements. How many functions are possible from A to B, and how many of those are injective? To answer the first question, let's make a sequence of choices of where to send each element of A. Although the ordering doesn't matter in a set, let's pretend the set is just the numbers 1, 2, 3, and 4 and go one at a time. Well, with no restriction on the function, there are 10 choices for where to map the number 1, then 10 choices for where to map the number 2, 10 for 3, and then 10 for 4. So there are 4 blanks with 10 choices. So that means there are 10 to the 4th, or 10,000 possible functions. That's not a k-permutation or a rearrangement, but just the basic multiplicative principle. However, if we require injective, then it's got to be less than 10,000. Let's count. There are 10 choices for the output for 1, but now only 9 choices for the output for 2 because we don't want them to collide. There are 8 choices for where we can output 3, and then 7 choices for where we get output 4. This gives us 10 times 9 times 8 times 7, which is 5,040 choices. You may not even realize it, but this is P of 10, 4, which makes sense in hindsight because we're basically looking at the codomain of our function and making a selection of 4 things out of it, and then putting the selection in order of which point in the domain maps to it. But I think it's actually clearer to not view this as a 4 permutation, but just count things and use the multiplicative principle. So in this video, we added 2 tools to our collection for counting: the factorial function for counting arrangements of items in a set, and the k-permutation for counting the number of ordered selections of k items from a group of n items. Next up, we introduce a new, but not entirely unrelated, counting problem of distributing items to different people.